introduction. I'm Kaiyu, and I'm a research scientist at Metafair. It's great to be here. And so today we're really in a kind of like an AI arms race. So you see leading players in the industry, like they are competing to release the next powerful large language models every few months. And interestingly, like math and coding seems to be at the center of this arms race, because, for example, OpenAI introduces an O1 model, and whenever they make new releases, they evaluate this model on a lot of the benchmarks, and many of them are mathematics. Like, for example, the AMI 2024 benchmark, which is a high school competition math in the USA. And similarly, Gemini from Google and Grok from xAI also highlighted their capabilities on math. And in November 2023, XTX Markets, which is a trading firm in the UK, launched the AIMO prize. That's $10 million for AI to win a gold medal in IMO. And not long after that, in the next year's IMO, in July 2024, Google DeepMind announced that its AlphaProof and AlphaGeometry have achieved the level of silver medal. So just, it's very close to the gold medal already. And even if we look beyond high school math, how about like more advanced research math? Epoch AI introduced this frontier math benchmark, which includes research level math problems collected by professional mathematicians. When the dataset was introduced, people thought it would be too challenging for AI. Like maybe we will wait for a few years to see any results. But actually, within a few months, when OpenAI introduced O3, it reportedly can solve more than 20% of the frontier math problem. So when we wonder why AI and math why math is important for AI. While math maybe it's intrinsically important for mathematicians, but it's not clear why AI companies should be caring about math. I see at least two reasons. First, math and coding are kind of treated as a proxy for complex reasoning and planning by large language models. And reasoning and planning, they're incredibly important for human intelligence, but they're still very, very challenging for the model. And if we have language models that can reason, that can plan, it can unlock unlimited number of applications. Like you can have the model help you manage your calendar or help you make travel plans. And second reason is that math and coding are relatively easy to evaluate. For a math problem, you can check if the result is correct, and for coding problem, you can run the unit test to see if it passed all the tests. Those evaluations are not perfect. We will come back to this point later, but at least they are reasonable. And if you think of like writing a crime fiction, it definitely requires complex reasoning in writing a crime fiction. Or if you compose a symphony, that definitely requires planning. But they cannot be reasonably evaluated. We don't know how good the language models are on those tasks. So that's why we work on math and coding instead. So we're going to briefly go over how current large language models are trained to solve math problems. So we focus on math, but our discussion also more or less applies to coding, and we will see later that math and coding are deeply connected. So at a very high level, math language models are trained using two main tactics, like supervised learning and reinforcement learning. And we will see that they come with different requirements. So first, supervised learning. So this is how it works. You start with a generic large language model. That's a massive neural network trained on the entire internet, not specific to mathematics. And then you wanted to learn more mathematics. So you expose the model to a large amount of mathematical content by further pre-training it on math-related websites or like web documents. For example, like from Math Overflow or from Archive. So now the model has seen more mathematics, but it still doesn't know how to like generate well-structured solutions to problems. So the next step, you fine-tune the model on a probably smaller data set, but the data in this data set are much cleaner. So they are problems paired with very detailed step-by-step solutions. And optionally, you can even further fine-tune the model to generate not only solutions in natural language, but also the model can use external tools like SymPy or Mathematica. So here is one example of what the data should look like. The data has a problem statement, and it has a solution. The solution has a final answer, but also has intermediate steps that leads to the final answer. And we're essentially training the model to mimic this kind of behavior, like using supervised learning. And as you can imagine, the most important thing here is the data set. We need a large and diverse set of problems with detailed step-by-step solutions. And collecting this data set cannot be fully automated. You need humans somewhere. And it needs a significant amount of human efforts. And this is what makes the data set really expensive. And the largest publicly available data sets for this particular purpose has around 900K examples, which is decent, but it's not a lot for large language models. And also, it's definitely not enough to cover like all possible mathematics we want the model to learn. And so as we see, the most expensive part in collecting this data is how do you get the intermediate steps in the solution, whereas the final answers may be cheaper. So another possibility is that so if we have only the final answer, we don't have the intermediate steps, can we still learn a model? So this is the second technique, reinforcement learning. And so we have the problem statement, we give it to the model. The model can generate a solution and with steps and final answer. And since you have the ground truth solution, you can check if the solution is, if the answer is right or wrong. So here it's right, but maybe the model can also generate an incorrect solution, and then you know it's wrong. So here you can, the verification is simple since you're just comparing the numbers. And so the result of this verification can be used as a reward for reinforcement learning. When it's correct, you can think of the reward is 1, and when it's incorrect, the reward might be 0. And we have reinforcement learning algorithm that can optimize the model to achieve high rewards. That is, the model will predict correct answers more frequently after training. And this idea is very simple and very powerful, and actually it's not new, it's decades old. But it's recently, it's gaining a lot of momentum because of DeepSeek R1 is the first to make this really work for training very large, reasoning large language models. And since then, this idea has like taken the language model world by storm. And just to see how much momentum it has, 1 month ago, the Turing Award was given to 2 pioneers in reinforcement learning. That's Dr. Richard Sutton and Andrew Battle. So when using reinforcement learning to do mathematics, the key is verifiability. To calculate the reward, you need to verify if the model-generated solution is correct. And this is easy if the problem has a numeric answer. You can just check the answer. But what about proofs? We will come back to this point later. So in summary, we have introduced 2 techniques for training math language models, supervised fine-tuning and reinforcement learning. Supervised fine-tuning is constrained by data, and reinforcement learning really needs the solutions to be verifiable. And data and verifiability, they will appear repeatedly throughout this talk. And I would say most or even all state-of-the-art math language models is really, well, conceptually not complex. It's just a very good pre-trained model, plus these 2 techniques, and more importantly, plus marvelous amount of engineering. So it's all about who has the better data set and who has the better infrastructure. And everyone is using more or less the same method. And given these techniques, are we ready to solve mathematics by AI? And obviously the answer is no. I was being intentionally very rosy when introducing how much progress AI has made on math, but there are many important gaps. First, existing success focuses on almost exclusively on pre-college math, such as high school math competition. And it's widely observed that language models still have a very long way to go for more advanced problems. For example, in Terry Tao's post, he tried ChatGPT with O1, and he thinks the model still struggle with the most advanced research math tasks. So you may wonder, isn't O3 already very good at the frontier math benchmark? Yes, but it comes with a few caveats. The most important caveat, I would say, is the problems in frontier math are designed to have numerical answers. Although they are advanced math, but they are designed in a way that all problems have a numerical answer. So this is just to make the evaluation easier, but it deviates from how mathematics is typically done. And this leads to the second gap. Language models are really good at guessing the final answer, but often struggle to show rigorously that the answer is correct. And according to Kevin Buzzard and also a recent study from ETH Zurich, state-of-the-art language models, they still fail miserably on Putnam and on the USAMO competition if you have humans to manually check if the solution, the proofs are rigorous. I think in USAMO it says it's about 5%. I think the more recent Gemini model is better than that, but still very far from perfect. And Kevin thinks the model can get at most 2 out of 10 points. And so here's an example of the kind of error the language model can make. So here we ask the model to prove a very simple inequality, and it used AMGM to derive the equation 70, which is correct. But then it tries to multiply the inequality, the both sides, by a positive constant, which shouldn't change the direction of the inequality, but then somehow the model flipped the direction. So this kind of error are kind of trivial if you pointed them out, but if you have very, very long proof, you want to check them step by step by humans, that's not going to be feasible. And we argued that language models alone, at least in the current form, is not sufficient to solve these gaps, like advanced mathematics and proofs. So here by language models, I mean neural networks trained to predict the next token using supervised fine-tuning and reinforcement learning. And they rely a lot on data and verifiability, as we explained. And unfortunately, or fortunately, in advanced mathematics, the data set is very scarce. If your mathematics is novel, it's very unlikely that you can find similar mathematics on the internet. And also, if you want to generate proofs using the model, the output is no longer a number, so there's no easy way to check it. And if language models are not enough, then what else do we need? And the research direction I've been working on for a few years, and which is also summarized in this recent position paper, is that we should combine informal data-driven reasoning in neural networks with formal and rigorous reasoning in formal systems. Here formal system includes different kinds of logics and computer programs, and specifically Ling. The role of formal system here is to verify the proofs and provide automatic feedback. And once you have automatic feedback, your model can potentially learn from the feedback without learning from human-created proofs, so which mitigates the data scarcity problem. And since you can verify if the proof is correct, you can rigorously check the problem and evaluate the performance of the model. So since this is the third day of the workshop, people have been probably familiar with Ling, so I will skip the introduction to Ling. And AI can be used in Ling in a few ways. One task we care about is theorem proving. So given the theorem statement, you want the model to produce a proof, and you use Ling to check if the proof is correct or not. And the second task is autoformalization, where on the left you have informal math written by humans, for example, in textbook and papers, and you want the model to help you formalize it into Ling. So in the rest of this talk, I will dive into a few projects on those two tasks, and we will start with theorem proving. And here's a widely used, maybe slightly old-fashioned recipe for neural theorem proving. Is to search for proofs using tactics generated by neural networks, including language models. So you start with an initial state you want to prove, and the model generates multiple candidates for the next step. And you run these tactics in Ling to get the next state. And you do that repeatedly So it explores a large number of states and potential proof paths, and until finally at some point you find a proof. Here, the search can be done using any search algorithms. You can use classic ones like depth-first search or breadth-first search or Monte Carlo tree search, and you don't need machine learning here. It can be purely symbolic. But the core is how do you generate tactic candidates? Here, the input is the local context and the goal. That's the current thing you want the model to prove. And optionally, the model can take a library of lemmas, for example, mathlib or other libraries. And you want the model to output a bunch of suggestions for the next tactic. So how do we train the model to do this? And a very obvious way is like we already have mathlib and other data sets, and that has a lot of human written proofs. Why don't we just extract data from those repos and train the model? Yeah, and this is actually not a new idea. People have been doing similar things many years ago, and like extracting data from human written proofs and train a machine learning model to predict tactics. It's actually way before language models or Ling were invented. But after we have large language models, this approach has become particularly promising. Because language models can really go beyond the formal proofs you give it as training data. When the language model was pre-trained, it has already seen a lot of mathematics, and presumably the mathematical knowledge it gained during pre-training can be used to guide the proof search process, which wasn't possible with older like machine learning techniques like KNN. So there are a lot of work in this direction. We will talk about one representative work using language models for theorem proving, LinDojo. It is very special because it was the first language model-based theorem prover that's fully open sourced. Anyone can access its code, models, training data, and tools for extracting data and for interacting with Ling. At a high level, well, it's very simple. You have Ling, and you have mathlib and other Ling repos, and you use LinDojo to extract a dataset. So the dataset consists of theorems and proofs, and tactics, and also lemmas, premises you can use in the tactics. And once you have the dataset, you train a machine learning model, and after it's trained, the model interacts with Ling to search for proofs. And in this particular work, we introduced a model called reprover, or retriever augmented prover. So the idea is we want the model to use not only the current state, but also the lemmas that's available in the library. So given the current state and given a bunch of lemmas, first we want to know what lemmas are more likely to be useful. So we encode everything as a vector. So the state is a vector, and every lemma is a vector. And we calculate their cosine similarity between the state and each lemma, so that we can pick the top ones from the library. So after you pick the top ones, you combine the retrieved lemmas with the state, and you give it to the model to generate the next tactic.
Very lossy encoding of lemmas as a vector with cosine similarity. That seems like a...
Yes. The question is this retrieval process very lossy because you are encoding everything as a vector? The answer is yes. The vector probably cannot capture the semantics of the theorem very well. I think here the decision is more technical because this architecture is very efficient. Even if you have a very, very big math library, to calculate the similarity, you only do one matrix vector multiplication. So it's very cheap. And so after LinDojo, we see many recent papers on neural theorem proving. Some of them also built on top of LinDojo. For example, DeepSeek prover from DeepSeek, intern LLM prover from AI Lab in China, and BFS prover from the ByteDance, that's the company behind TikTok. And recently the Grader prover from a team in Princeton, and so I'm also playing a small role in that team. So they improved upon LinDojo in several ways, and I think a recipe that have been verified to work well is we want more data. Instead of just having data from Mathlib, we have the model synthesize more theorem statement by autoformalizing like informal mathematics. And once we have a large collection of formal statement, we can train the prover by what they call expert iteration. So here is how it works. Imagine I have a lot of statements, but I don't have the proof. And then I have a prover. Initially, the prover may not be very good. I use the prover to try to prove things. But maybe I'm lucky. Finally, I will get something proved, some theorems proved. And once we have some theorems proved, I add the proofs back to the training set. So now I have a bigger training set. And use the big training set, I train a better prover. And then you iterate. Iteratively, you find more proofs. And here the results shows the x-axis is the number of iterations you do. As long as you do more iteration, you have more data, and the performance generally goes up. However, can we do this like infinitely so that we can prove every theorems? Well, the fact is that if you do that after a few iterations, it will saturate. And because there are limitations with this approach. So first, language models really needs a lot of data. But still, back to the original point, if you want the model to do some novel mathematics, you are unlikely to have data. So that's why if you create a new repo in Lean, you want to formalize your mathematics, the mathematics you are interested in. And if you use these models off the shelf directly, very likely it's not going to work that well. Because your models might be very different from Mathlib, which was used to train the model. And the second issue is the action space in proving a theorem is very big. So if you compare theorem proving with playing Go, why is theorem proving different? Why AI can do well on Go, but not yet on theorem proving? One fundamental difference is the action space of Go is smaller than the size of the board, which is 19 by 19. Whereas the action space of mathematics, that's the potential thing you can do when proving a theorem, is infinite. And since you have an infinite space, it's very difficult to try to cover the space by using human-created data. Or even if you are doing reinforcement learning, it's very difficult to explore the space very effectively. So how do we solve the problem of, how do we deal with infinite action space? We did some very preliminary exploration in that direction, and in a very constrained domain. That's elementary algebraic inequalities. So the problem we consider is this kind of theorem. So you have a finite number of real numbers, like ABC, and they satisfy maybe some precondition, and then you want to prove inequality. So if you think of how humans do this kind of problems, they typically apply existing lemmas like Cauchy-Schwarz or AMGM, and sometimes they rewrite their formula in some clever way so that an existing lemma becomes applicable. That's the main techniques. Even though the number of techniques is relatively constrained, the search space is still very big. Like for example, for this inequality, you could apply AMGM in multiple ways, and you can apply other inequalities like the T2 inequality, and you can rewrite this inequality into another form, and there are many possible ways to rewrite it. So if you want to search for proofs in this space manually, then it's infeasible. And we actually also tried, okay, can we give the problem to large language models like O1 and O3? And they're actually doing pretty badly. So we give it to O1 and O3, and we manually have humans check the solution. We checked about 20 problems. We cannot check more because checking the solution is very difficult. It needs a lot of human effort. The result is that O1 solved none of the 20 problems. O3 and R1 solved 3 or 4 problems, whereas a human trained for this domain can solve around at least 15 problems. So then how do we get a machine learning model to do this? We want to learn from how mathematics or humans do to prove this kind of inequalities. And we categorize the techniques they use into 2 categories. One is called scaling. Scaling is you apply an existing lemma, like Cauchy-Schwarz. Here's an example. So on the left, you have AB plus BC plus CA, and humans can realize that, okay, this matches with Cauchy-Schwarz, and if you apply Cauchy-Schwarz, you have reduced the problem to the inequality on the right. So that's scaling. You're essentially using Cauchy-Schwarz to scale the left-hand side of this inequality. And you can apply different lemmas, and each lemma can be applied in different ways, give rise to a lot of potential reductions of this proof goal. But what's good about it is you realize the number of scaling you can do is not infinite, it's finite, because there is finite number of lemmas, and each lemma can be applied in finite number of ways. So it's possible to enumerate all scaling tactics. And then after you enumerate everything, some of them will lead to results that's obviously wrong, because sometimes you scale things too much, so the inequality becomes wrong. You can try to remove those wrong ones, and you end up with a relatively small set of next state after applying the scaling tactics. Besides scaling, another class of tactics you can do is called rewriting. That you transform the formula into something different, into an equivalent form. So here, it's tricky that because the number of potential rewriting is infinite. Given any formula, you can write it in an infinite number of ways. So that's why we cannot enumerate it. And we have to use large language models to propose rewritings that the models think may be effective. So, for example, here we have a inequality, and we have a prompt. We give the language model the prompt and the inequality, and it rewrites the inequality to the one on the right-hand side. Well, in practice, our system is slightly more complex. We don't have only one prompt. We have different prompts for different kind of rewriting, but this is how it works at a high level. So just to put it together, we propose a method called LLMs, which is LLM-based inequality prover with symbolic reasoning. And at a high level, given the current inequality you want to prove on the left, we use symbolic algorithm to enumerate all possible scaling. And we use language models to generate a set of rewriting. And those tactics, they lead to the next goal, and we use SMT solver to filter the goals to remove the ones that are incorrect. And now we are left with a set of reasonable goals, and then we iterate and try to predict the tactic for the next step until we have solved the problem. And here's a very simple evaluation. On the 20 problems that we have checked manually, like LLMs can do 16 problems, which is similar to what human gold medalists can do. And we also evaluated the method on 3 benchmarks from prior work. And on the last column is LLMs, and we compare it with existing neural provers and symbolic provers. It ended up that neural provers are pretty bad on this task, and symbolic provers are much better. Like you use Mathematica or use SMT solver, they can solve pretty non-trivial inequality, but still they are not as good as LLMs. And we find a very interesting proof that's from the book of Ivan Chen, who was an IMO coach for the United States. So he mentioned that AMGM alone is hopeless here, and he came up with another proof. But we find that the proof found by our algorithm uses only AMGM and combined with some clever rewriting. So here's the takeaway. So it's a very simple domain, but I think it shows that the challenge in theorem proving, or one challenge in theorem proving, is how do you effectively explore infinite action space. And it tells us if you have a particular area of mathematics that you care about, you know a lot about this particular mathematical domain, to structure the human actions into some well-structured way so that it becomes more feasible for the machine learning model. Although it's an open question whether this can really be generalized to many different domains. Okay, that's theorem proving, and I will talk about autoformalization next. if you have any questions, just feel free to interrupt.
For the inequalities, what kind of mistakes did O1 make when the human evaluated?
The mistakes are usually not super subtle. One is the example we have already showed. Like when you multiply a positive constant to the inequality, you shouldn't change the sign, but it changed the sign. So that's one error. And another error I've seen, it tries to invent reasoning patterns that are obviously wrong. So one example is now I have to prove the summation of three terms, a plus b plus c, is greater than 0. And the model tells me, okay, A is positive and B is positive. C, I don't know, but as long as two terms are positive, very likely the result will be positive. So things like that, yeah.
They're fundamental reasoning mistakes.
Yeah.
So does your system kind of learn correlations between different tactics, or so applications of either the scaling, which lemmas, if you applied, lemma A and lemma B, is it likely then, a certain lemma C will be useful in a context? Does it learn like sequences of?
Currently, it's not. Currently, we are predicting each step independently. You're not informed by previous steps. Yeah. So we probably have to go on because there are other content. So we've covered theorem proving, and we are going to talk about autoformalization. In autoformalization, you have informal math on the left, and you want to generate formal math on the right. And there are different things you want to generate. One is the theorem statement. For example, you want to translate there exists an infinite number of primes to this formal theorem statement on the right. And there are proofs. So you want the model to take the informal proof and give you the formal proof. And actually, these are two subtasks, and they have very different challenges. So let's talk about the theorem statement first. For the theorem statement, a major challenge is how do you even evaluate the results? Here, you say, okay, we have an infinite number of primes, and the formal statement says, for any natural number n, there exists like a prime number p that's greater than or equal to n, which is correct. But it's not the only correct solution. For example, you can make it slightly different. You can change greater than or equal to strictly greater than. Or you can say, okay, for any prime number n, there exists a prime number p, blah, blah, blah. So as humans, you can easily see they look slightly different, but they're essentially the same thing, and all of them are correct. But if the model produces one of them, how do you know if it's correct or not? You may say, okay, can we have a ground truth, and we check if the model-generated statement is logically equivalent to the ground truth. Well, this is good, but unfortunately, we know from theoretical computer science that this kind of equivalence checking can be infeasible in general. So that's why in practice, people resorted to human evaluation. You ask human to see if it's correct, and also or proxy metrics like the blue matrix. And human evaluation is very expensive and not scalable, whereas these proxy metrics, they are not very accurate. So that's the challenge with autoformalizing the statement. So how about proofs? Proofs, the problem is even the most rigorous human-written proofs are not rigorous enough to the standard of Ling. So there are all kinds of gaps, like mathematicians often say, okay, this case is left to the reader. And so this is kind of like explicitly stated gaps. And there are even implicit gaps, which we will be talking about later. But as long as there are gaps, like when your model have to fill in the gap. And this can be very challenging for the model. So we have two challenges. For theorem statement, we don't know how to evaluate. For proofs, we need to fill in the gaps. And in this project, we want to address those challenges together. And this sounds very ambitious, but what we find is things that's intractable in general, they can be made tractable if you restrict to a very specific domain. And here, the domain we choose is Euclidean geometry, because it's just a very old branch of mathematics that's used to test humans for thousands of years. And recently, you have alpha geometry, which makes it pretty promising benchmark for theorem proving. And in this work, we show that Euclidean geometry is not only a good benchmark for theorem proving, but also we can use it for autoformalization. And concretely, we introduced a benchmark called Ling Euclid that's for autoformalizing Euclidean geometry. It includes 48 theorems from Euclid's elements and also more than 100 theorems from another data set. And we have, it also comes with the proofs. So let's see one example in our benchmark. So that's proposition 1 from Euclid's Elements Book 1. You have the diagram, you have the statement, you have the proof in natural language. And when constructing the benchmark, we manually formalize this statement and proof in Ling. And the result is looks very similar to the informal proof in the sense that there's a one-to-one correspondence between the tactics and what's being done in the informal proof. I think this is very beautiful to me because we believe we are one of the first to faithfully formalize the proofs in elements in a proof assistant like Ling. And by faithfully, I mean there is a direct correspondence between what Euclid has written to the tactics in Ling. Because if you, some people have formalized Euclidean geometry using other foundations like Hilbert's or Tusky, but they cannot maintain this one-to-one correspondence. Question?
So you said your system formalized 48 of the statements, or the benchmark itself only contains
the benchmark. So we are not talking about the model yet. And this,
so like Euclid contains like 400 statements, right?
But book 1 has only 48.
Oh, I see.
Yeah.
I see.
Excuse me, that's not true. I and my 2 colleagues have published complete formalizations of Euclid Book 1.
Like in Coq or?
They were in a custom theorem prover, but then translated into both Coq and whole light.
Okay.
I'll give you the reference.
Yeah, I will try to read the reference. And okay, and here.
Can you expand more on the one-to-one correspondence?
What I meant was, well, maybe not even technically one-to-one. What I meant was there's a correspondence between the tactics in the formal proof with the text Euclid have written. So you're not trying to come up with another proof of the theorem using other axioms. You are exactly following what Euclid was doing. Okay, and during this process, we did find a few errors made by Euclid. I will show one example here. So this is proposition 24 from book 1. The theorem says, okay, you have 2 triangles, and they have 2 edges equal to each other. So AC equals to DF, AB equals to DE, and the angle A is bigger than angle D. So you want to prove BC is bigger than EF. So this is, let's try to replay Euclid's proof. So first you move the triangle on the left to overlap with the triangle on the right. So C becomes G. And then you connect G and F. So now you only have to prove like EF is smaller than EG. And it's easier because now they're in the same triangle. And a previous theorem in the book says, okay, in the same triangle, a bigger angle corresponds to a bigger edge. So now you only have to prove the bigger edge here, EFG, is bigger than the smaller edge here, the EGF. And then that can be proved by realizing that the triangle DGF is isosceles. So you have these 2 base angles of the isosceles triangle, they equal to each other. And now you see the big angle is bigger than the DFG because it's like a superset of it. And the DFG is equal to DGF, and the DGF is bigger than the smaller angle. So you are using this as like the angle in the middle. And now it's done. So anyone disagree with this proof? No? Oh, it's isosceles because the DG equals to AC, and AC equals to DF.
What if D is longer than DF?
Sorry?
D is much longer than DF.
No, DFG is isosceles. DFG, so DF equals DG, not DFE. Okay, so the question is, the proof is correct for this particular diagram, but what if it looks like this? So let's replay the proof. First, move the triangle on the left to the right. Second, connect G and F. Now you still have an isosceles triangle, so you know DFG is isosceles. You have two angles alpha, they are equal to each other. But now you have to prove x is greater than y. So now it's tricky because alpha is no longer inside x and y. It cannot be used as the angle in the middle anymore. So we have to fix this proof manually, and luckily it can be fixed without much trouble. So first you realize DGE is alpha plus y, and it's an inner angle, so it's smaller than pi. And then you realize DFE, that's 2 pi minus alpha minus x. It's also an inner angle of a triangle, so it's smaller than pi. If you add them together, and things cancels out, and you know x is greater than y. So it's not difficult, but it's different from what Euclid was doing. So that's why we say, okay, so here are two cases in this proof, and Euclid seems to focus on the easy case and ignore the more difficult case. Okay, that's maybe probably a...
Is this the first time anybody found an error in this proof? Or?
I don't know. I believe if this proof has been formalized before, people may have found it before.
Even without formalization, I would imagine people would have.
I don't know. But I've read, I'm not about this particular one, but if you read, I don't remember the name, but someone from ancient Rome, they write a book, like a follow-up on elements. And in their book, they have already found a few errors similar to, whose nature is similar to this one. So I imagine maybe among these 2,000 years, there are also other people like Apocalypse, yeah, Apocalypse. Okay, so that's a digression, but it shows like how formalization can potentially help you find holes. And so back to our benchmark. So in our benchmark, we want to evaluate whether the model-generated statement is equivalent to the ground truth. And we find that using SMT solvers to prove these two theorems imply each other can give you a reasonably good metric of whether they are equivalent. And here, maybe the reality is more subtle than it shows, because so if as long as both theorems are correct, both of them are true, then they imply each other by definition. But I don't want to say, okay, any two true theorems are equivalent. And the secret is here, we don't want SMT solvers to be infinitely powerful. We don't want it to be able to prove any equivalence. We want it to be able to prove only equivalents that are trivial or easy to prove. So I think this is fundamentally not a mathematical problem. It's more like empirically whether SMT solvers work good enough, but not too good. Okay, so that's the theorem statement. And then let's talk about the proofs. Because if it's too good, it can prove the equivalence between any two true theorems, even those two theorems has no relationship at all.
It's also equivalent to 2 plus 2 equals 4.
Yeah. So that's the...
Whatever direction SMT solver would find, like the constituent steps would have to be kind of much more primitive than the level of complexity of each of the statements you're trying to prove equivalent.
Yeah. So what's the question?
So I mean, like one way to kind of maybe formalize this idea of not having the SMT solver being too powerful is you could like restrict to a much more primitive set of steps and tactics that.
Yeah. I think the idea is you don't want it to be like a universally universally valid automated theorem prover. It has to be restricted. Yeah. Okay, that's the theorem statement. And then let's talk about the proofs. For the proofs, the reason we choose Euclidean geometry as a domain is the there is a well-defined or relatively well-understood type of gaps in Euclidean geometry. That's diagrammatical reasoning gaps. So one example, Euclid's proposition 1, you have two different points A and B. It's possible to construct an equilateral triangle. And this is Euclid's proof. First, you draw a circle centered at A, and B should be on the circle. And then you draw a circle centered at B, A should be on the circle. And then you pick their intersection, and you connect everything. That's an equilateral triangle. Anyone disagree with this proof?
Well, that proof has been criticized for
for a lot, yeah. So the reason is you didn't prove C actually exists. You didn't prove these two circles has intersection. And this is proposition 1. So you can, if you want to prove it, proposition 1, you can only use the axioms. And if you try to use Euclid's axiom to prove C exists, well, I believe it's not even provable. But no one bothers to prove it because it's just obvious in the diagram. But that's problematic if you want to formalize this proof in Ling, because Ling does not know what is a diagram or what is obvious in the diagram. So you have to kind of formalize the notion of what is obvious in the diagram, and that leads to, I believe, Jeremy's work. So that's how I got to know Jeremy like many years ago, and thanks a lot to Jeremy to provide a lot of feedback on this project. Jeremy in 2008 proposed this formal system E. I understand it as, maybe Jeremy can correct me, it's kind of like a set of unspoken axioms. And being obvious in the diagram is modeled as, so if a fact is obvious in the diagram, then it's a logical consequence of this kind of, this set of unspoken axioms. And these axioms include trivial facts like, I believe the first one is, okay, if C is the center of alpha and B is the center of alpha, then A and B should be the same point. So like a circle cannot have two distinct centers. So this is not in the Euclid's axiom, but it's just so obvious. So in this work, we try to implement this set of axioms, like the diagrammatic axioms, and we use SMT solvers to do automated reasoning to derive the consequences of these axioms. That's the facts that are so-called obvious in the diagram. So let's put it together. So we have a benchmark that's manually annotated. In the benchmark, we have a ground truth theorem statement. And we want to use machine learning to generate a formalized statement. And once it's generated, we evaluate it by using SMT solver to check the equivalence between the ground truths. And that's statement formalization. And for proofs, the model can generate a proof. And we give the proof to Ling. It will tell us a list of reasoning gaps that cannot be checked. And then we will give those gaps to SMT solver to see if SMT solver can fix all the gaps. And if yes, then we see, okay, this is a valid proof. And I believe there were a few prior work, like trying to formalize Euclidean geometry. Like one I'm aware of is called GeoCalc. It's like formalizing Euclid's proofs in calc. But what they are doing is different from here in the sense that they have humans manually fix all the gaps. They don't use SMT solvers to fix gaps. So as a result, the proofs is much, much longer than the original proofs in the Euclid's book. And so that's the benchmark. Then we also did some very simple experiments, but that's probably not the focus of this paper, but just some very nice benchmark results. So here we tried GPT-4 and GPT-4 Vision. So GPT-4 Vision also takes a diagram as input, and GPT-4 only takes the text. And we see that green is better than blue, which shows taking the diagram helps at least a bit for this model. But still, it's even the best model is like around 20%. That's the success rate for formalizing the statement, which shows the statement formalization is still a very challenging problem. And here's the takeaway for this project. We have two challenges in autoformalization. For the theorem statement, we don't know how to evaluate. And for the proofs, it asks the model to fill in too many gaps. And in this particular domain, Euclidean geometry, we find that we can leverage SMT solvers and also system E to try to kind of address both problems, using SMT solver to check the equivalence and also to fill in the diagrammatical reasoning gaps. And but still, I think related to theorem proving, the open problem is how do we really generalize this to different domains? In another domain of mathematics, maybe there are different kinds of gaps or different kinds of reasoning patterns that are not covered here. And can the model, can we devise a general algorithm that can work well? That we don't know. And great, so that's the end of this talk, and I'm happy to take questions.
Thank you for the great talk. I'm just wondering, what do you think is the future work should do in auto theorem proving? Because there are two options, right? The first one is to synthesize more data, just like what you have done in your golden prover. And the second one is to like design a more efficient and high quality like scaling time tactics, like you just like what you've just done in your LLMs. So what do you think is like better in the future?
Repeat.
Okay. The question is, in neural theorem proving, which way should we go? Should we synthesize more data, like we did in the Gödel prover, or should we devise a better algorithm to search for proof during test time? I think, well, both of them will work, but I particularly think synthesizing the data is the way to go. But I think the caveat is the current way of synthesizing data, like as done in DeepSeek or in Gödel prover, it's kind of like well, it's nice to have, but it's a low-hanging fruit. What I'm really want to do is how can we synthesize the theorem statement by generating conjectures that maybe not maybe humans haven't proposed yet, instead of only trying to translate from human-written informal math to the formal math. Because even the amount of human informal math is much bigger than formal math, but it's still limited, it's still finite, whereas the space of potential theorems you can write is infinite.
Thank you.
So am I understanding correctly that you have proven Euclid's theorems from Euclid's axioms and Avogad's axioms?
Yes.
So, but Euclid wanted to be like lean with efficient with the axioms. Have you considered what's the minimal set of axioms that is capable of
the question is, have we considered what is the minimum set of axioms to formalize Euclid's geometry proofs? The answer is we didn't, and also in particular, I believe in Jeremy's paper, Jeremy also mentioned the axioms in system E was not designed to be minimal. So there might be redundancy between the axioms.
Have you thought about taking auto-informalization, so basically going from either formalized propositions or both, or different kind of things between back to natural language, because then you can have LLMs which are good in natural language, and often many problems outside mathematics are not so formal. They're kind of more fuzzy in their requirements.
The question is, have we considered auto-informalization? So that's the reverse of formalization. You go from formal to informal. Yes, I think that's a very promising direction. There are at least two ways this can be useful. One is you can generate natural language explanations of formal theorems. That's for mathematics, or for students trying to understand what this formal theorem is doing, or this proof is doing. And so that's useful for us, although it's not. There's no easy way to evaluate if the explanation is useful. And the other aspect is we can treat this as a way of generating data. We can generate more paired informal-formal data by doing the reverse auto-informalization. And when it comes to generating the data, we can always evaluate, okay, is this data set useful for some downstream task?
Yeah, I was just thinking beyond that, from a commercialization standpoint, beyond mathematics. Many problems they don't care exactly what you solve if it's kind of good enough. So you can create products which are closer. So That's the angle there.
I see. So yeah, I believe that will be also useful for that angle, especially well, given that a lot of the mathematical reasoning and planning applications, you don't need it to be like 100% formalized.
So thank you for a lovely talk, and I'm delighted that the work on geometry has come to fruition. I would just feel guilty if I didn't mention my co-authors, who are Ed Dean and John Rubal, who are also
on the System E paper.
So I was curious. So my students use ChatGPT to do proofs very often, and these proofs are not always correct. So what is the nature of these errors? Like I was thinking, like before your talk, that it was pure hallucination of LLMs, but now after listening to your talk, which was wonderful, by the way, thank you. I'm now wondering, was the current version like trained specifically for math problems, and is maybe the nature of these errors is somewhat different? It's not just hallucination, but the way how we can do math so far automatically. Can you comment on this?
I think the question is, well, what's the nature of the proof errors language models are making when generating proofs? So why they're making this kind of errors? So this is only speculation, because we like language models still largely a black box. I believe the error comes down to how language model is trained. So when the model doing pre-training, it has seen okay, maybe some internet data sets have some proofs, have some mathematical proofs in the data set. So the model can try to mimic. And then after pre-training, there is a process called alignment or reinforcement learning from feedback. So that's you ask the model to generate multiple responses, and then you ask humans to rate, okay, which response I find is better, it's more useful, it's more helpful to me, and then you optimize the model to be kind of satisfy the human to produce like a very nice response that a human will give you a high rate. And when it comes to generating mathematical proofs, I find the model will try very hard to find a nicely looking proof, like a plausible proof that, well, maybe a non-mathematical human will say, okay, this looks really good. But it really has no signal to learn like what is valid or versus invalid reasoning in the proof. And whenever it cannot find maybe a valid proof, it will still try very hard to try to satisfy the human, like maybe kind of like try to touch it up a little bit and make it more subtle and make it more like a real proof.
What do you think is the harder problem, informal math or formal math? Because in formal you have the feedback from the system, but also the requirements are much more stringent.
Mm-hmm. The question is informal math harder or is formal math harder? I think we don't necessarily have to choose between informal versus formal. I really believe in the future of language models for math, we will combine both. We will use the informal math language model has learned during training as kind of like a guidance, but we want to ground everything in a very nice formal system so that everything can be checked very nicely. And well, if you look at existing progress, yeah, most of them are on informal math, but yeah, they are also on like high school problems and problems that don't require you to give a proof. And we really believe in order to go beyond that, you need to incorporate formal math, but it's not like you have to switch to formal math.
Thanks for the talk. I guess you seem to specialize on, you work on specialized automated theorem proving systems, ones that work specifically within domain, and like inequalities and geometry. I was wondering, if you want to move forward on this, if you want to create a system that's general, would this look like you train, for each domain, you have an expert, and then they're all superhuman within that domain, and then you use perhaps a mixture of experts to combine it all together? Or do you think it's better to just have sort of one model, it does everything?
The question is, should we build specialist mathematical agents that's tailored for each domain, or should we build generalist mathematical agent? I believe it's a really good question, and I think in the near future, that's at least within this decade, both research programs will coexist. Whereas in the long term, yeah, at least the taste of AI people is to, okay, we really want to strive for being very general. We want the AI to do, eventually it tries to figure out like the insights in each mathematical domain in a general way, like some human mathematician can do. But I would acknowledge in the short term, if you want to do well on a specific task you have in mind, your best shot would be to add a lot of domain-specific insights.
Let's take a couple more questions.
So, you mentioned alpha geometry. Do you know what alpha geometry is able to do with Euclidean like Euclid's elements, propositions?
Alpha geometry focuses on proving the statement, and the statement it can prove is like IMO problem, so which is much more difficult than Euclidean geometry problem. And here our focus is on how can you build a foundation, like try to formalize everything in Ling. Whereas in alpha geometry it doesn't use Ling, it's kind of invented its own like domain-specific reasoning system, which does not have to be like grounded in a sound way and back to the axioms.
Oh, so alpha geometry doesn't have a rigorous.
It's not built on top of Ling.
But how are the solutions currently being verified?
They define some like predicates, and also some domain-specific language and some inference algorithm to do inference in this language, but it's not verified, so we don't have guarantee.
But presumably you could, just within the realm of geometry, Euclidean geometry, you can, given not just Euclid's proof, but given some proof coming from somewhere, then you could presumably formalize that using your.
Yeah, presumably, if all the rules and axioms in alpha geometry are sound, and if you have enough engineering effort, it should be possible to rewrite everything in Ling or compile the solution into Ling.
So there's been kind of some, you've been working here on like autoformalization to try to like improve on the kind of problem that we have, which is like lack of data. But then of course there's also generation of synthetic data that has been showing some promise as well. Which like sort of aspect do you think would be like more useful going forward? I guess it's not necessarily a comparison, but which one do you see showing more promise in the long term?
The question is autoformalization more promising, or is synthetic data generation more promising in terms of producing more data? I think it depends on what synthetic data generation you mean here. Autoformalization can also be a form of synthetic data formalization generation, but I would assume like synthetic data formalization could mean, okay, we generate theorem statement like what we do in alpha, what they do in alpha geometry. I think by synthetic data generation in this way, you can generate potentially a bigger set of data. Like in alpha geometry, they generate like I believe it's like around 100 million theorems and proofs. Whereas if you collect all the like Euclidean proofs humans have written, it's not nearly as much. But the problem is for generating synthetic data, you seem to need a domain-specific algorithm. Like in alpha geometry, I believe what they do is, okay, I sample a few points, I sample a few circles, sample some lines, and do so that I have a diagram, and then I do some symbolic reasoning on the diagram, and then I do some filtering, and this becomes an example in the data. Obviously, this only applies to Euclidean geometry. You don't apply exactly the same algorithm to another domain. So how do you build a domain-general synthetic data generation algorithm? That we don't know yet.
Yeah, so let's continue the discussion to better the coffee break. We restart at 11:30. Let's continue the discussion.